Well, thank you for having me here again. It's been a few years, and it's great. You guys are a very fun crowd. A couple of disclaimers, and then we're going to do something a little different. Disclaimers. What I'm about to show you is experimental. It may or may not ever be standardized, but I hope it will. I have not shown it to the committee as a whole yet. I've been working on, for the last 2 years, about 2 years ago, I made a decision that there are many things we can all work on, far more than we possibly could all do. And I made the decision I was only going to work on things that would make C++ both more powerful and simpler to use. And if you think that's an oxymoron, don't leave before the last slide. And this is one of the results of that work over the last couple of years. You're going to see a live compiler demonstration. I want to call out especially Andrew Sutton, who also implemented concepts in GCC, for doing that implementation. So thank you very much to Andrew for that. And again, the C++ committee will see this in the summertime, and we'll see what they say. The syntax is malleable. It will certainly change, even if they like it, and I hope they like it, but we'll see. In the meantime, let me share some thoughts. But before we do that, for about 10 or 15 minutes, I would like to, if it'll be all right, invite two people to the stage who don't know anything about what I'm going to say, and do a little UX study with our backs to you for 10 or 15 minutes that you can just watch in on, and then we'll start the talk, if that's all right. Sorry about the turning the backs part, but it helps them feel more private and less scared. So I'd like two volunteers, please. One who has less than 5 years experience and one with more than 10 years experience who are willing to be on camera, because this will be on YouTube, you have been warned. So could I have your, who is like less than 5 years experience? Please share. Okay, could we invite you up? They'll mic you up, and more than 10 years experience, who's willing? And, oh, by the way, I meant to say that there's an important proviso. It has to be somebody, so a few members of the Standards Committee have seen this. It has to be somebody who has never seen it before, does not know what I'm going to talk about, who's going to see it cold, and is not a member of the Standards Committee. Seriously. Well, there are a few of you here. So with that, and so you fit that? Excellent. And so more than 10 years experience, please? Volunteers? Hey, not somebody I recognize. In the back, please. Will you come up? In the meantime, would you stand up and introduce yourself? What's your name?
Ina. Hi, nice to meet you all. Can you hear me? Yes, so I have been at the conference for the last 2 years, thanks to John. And yeah, it was pretty much.
You won't be sitting in front of that. Okay. Come right up. Come right on up. Thank you. And so, have we met before?
No, you know.
Hello, Herb. Have you seen anything on this? Have we talked about these slides? Have you seen any papers? Do you have any idea what's coming?
I would be the last person to actually know what that's about.
Please have a seat. And yourself, this is Arvid.
Arvid, yes.
Yes, would you please introduce yourself?
Well, I'm Arvid. I'm a software developer at a company that does inspection machines for the pharmaceutical industry. There is apparently something wrong with my wiring up.
That's great. And have we met before?
Never.
Okay, I didn't remember. My name's Herb. Well, nice to see you.
Nice to meet you.
And have we spoken about this material? Have you ever seen anything about this?
I've never seen any of this.
Please have a seat.
Thank you.
Now, pardon us for turning our backs and ignore these friends of ours. We'll include them again in a moment. So we're doing a small user study. We're exploring a potential new language proposal for ISO C++. It has not been proposed to the committee yet, but we're working on it, incubating it, and if it is accepted, if it succeeds, best case, it would be available on all compilers and platforms, so you don't have to worry about compiler dependencies or vendor lock-in. I'm going to show you 3 code examples, and the purpose is we want to see how you react to them and what you think, so there are no right or wrong answers. Please just think out loud, ask questions anytime so we can hear how you're reacting to them, how you're processing what you see. Some of the code examples will be side by side with existing today's C++ on the left and something new on the right, and some will be entirely new. So, here's the first one. On the left-hand side is today's existing C++ code, and on the right is a proposed way of writing it perhaps in a future C++. What do you think the code does? Tell me what you're thinking as you look at the code. What do you think it does or means?
Currently, what's existing is actually a lot more complex. And for a person who's not dealt much with C++ at all, and I can see what it's trying to do, but it's definitely not that easy to convert from an object-oriented language to actually using that. And on the side, it looks a bit more like what I've been working with, at least, which is C#. So
When you say it's what you can see what you're trying to do, what is it you're trying to do, do you think?
So I've got a shape, and then I want to be able to scale it. I want to be able to get the area of that.
Well, to the left is basically an interface, a virtual interface, a virtual base class, in the style that C++ has done this all the time. And to the right, I see something which, well, looks a little bit cleaner and more like other languages do it.
What do you think is the accessibility of the functions, the access specifier on the functions on the right?
That's public.
Public,
Yeah.
and to the left, it's probably something implicit. It's probably meant to be public as well.
So if I told you that the right-hand side was identical in meaning to the left-hand side, which one would you feel more comfortable writing? You know the left-hand one. Which do you think, what are the benefits or costs of each one, in your opinion?
I'd definitely go for the right one, just because it's easier to remember, like less code to actually type, and it's closer to language, really, to our everyday language, rather than this. So.
Yeah, I probably would prefer the right one as well. It's much cleaner and less typing, yes.
Yeah.
So you both mentioned cleaner and less typing. Do you think that one or the other might be more prone to errors or unintentional mistakes than the other?
Certainly the left, because if there's more to type, there's more errors you can make. I think the right would be less prone to errors, certainly.
Yeah, I definitely agree with that.
What kinds of errors do you think are possible in one side and not the other side?
On the left, you could leave out
Exactly.
you could, by mistake, not make them pure virtual, and then you would have problems.
And there you're actually relying on the compiler or whatever is actually executing that code to deal with it for you, so you don't need to worry about it, and you can leave it by default. And in here, you've also got more syntax errors to actually make as well.
One last question before we leave this slide. If this idea of an interface were proposed to be added to the C++ language so that compilers would know about this special thing as in some other languages, do you think that would be a good thing or a bad thing? How would you feel about that?
Certainly yes.
Wouldn't necessarily say it's a good thing, because a lot of programmers actually prefer to have that control, so they don't want other stuff deciding for them what to be used and when. So it might be like a trade-off in between, like whether you actually get that control or you let something else decide for you.
Okay.
But in the proposal wouldn't be to remove this, right? It would be an added.
Oh, we would never take we would never take anything away from you. No.
I wouldn't be surprised if you tried to do
Yes,
that.
I was hurt last time I tried to take something away from a C++ program. I'm just kidding. I was not stupid enough to try. So thank you. So this showed left and right today and tomorrow potentially. The next one shows code that does not exist at all today, so it's just all new, and it will be syntax you've never seen before. Please talk out loud and tell me what you think the code means. So what are you thinking?
Well, it's not particularly clean.
It's a bit overwhelming, let's say.
Mm-hmm.
Some requirements are being put or communicated to the compiler in a way that may be quite readable to the compiler, but not so much to me, I must admit.
Okay. So when you see in the first compiler require that you're talking about, it says $interface, if I told you that that meant reflect on interface, meaning the current class type, and its member variables, and if they're empty, print this string. If that's not true, print this string. Would that make sense to you?
It would make sense, yes.
Then what do you think the other two compiler requires do?
So if there's that instance of the interface, or
Probably talking about copy or move semantics
Yeah,
here,
exactly.
I would expect. And yeah, interface is okay. Well, it says it there. You only have to read it.
In the if toward the bottom there, where it says if f not has access, f make public, what do you think that does?
or if you don't have enough, I don't know, enough access to that instance, then just make it more accessible. That's what I would get.
Basically, it says it has to be public,
Yeah,
right? Because
exactly.
an interface doesn't make sense really if it's not public.
Okay, so if I told you that f dot has access means has an access specifier specified by the programmer. So if it's default,
Yeah.
then
Yeah, makes sense.
so what if I told you that this was the proposed implementation of the interface you saw on the previous slide as code, not as a language feature?
I'm not quite
I wouldn't agree.
takes some getting used to, but
Yeah.
everything is there, yes, but it's, well, it's not somewhat verbose.
So if I were to explain it as follows, that this is saying there's a metaclass, and you can give it a name, and you can write your own as well, but this metaclass named interface always has a no except destructor, and it requires that there's no data members, no copying. If functions don't have an access specifier, we make them public by default, and we require there are no non-public ones, and that all functions are pure virtual. And so that on the previous slide, if you say interface instead of class, it means this specialized kind of class. It's still a class, but just applying these rules. Would that make sense to you?
Yeah.
Yes?
It does. It explains how it happens and how it knows and decides what to do.
So if you could use this feature to write metaclasses of your own, can you think of, would that be interesting to you? Can you think of ways that you might use that?
I think it would be interesting, yes.
Why? What interests you about it?
It would be a very flexible way of writing interfaces. I could.
I think it gives you back, because I mentioned that programmers actually enjoy having that control. This gives you back the control, and it gives you a way of actually making sure it's always doing what you wanted. So I think it's actually quite, if that is actually what it does and what it's supposed to do, I think it's doing its job well in that case.
So what if you had this potentially, some of the common ones in a standard library, and you had your own in-house style of interface? Would it seem reasonable to write rules for that and have your developers use those?
Yeah,
I
definitely.
think so, yes.
Do you think that would be better or worse than what you do today? And why?
I think it will be better. Basically, following a specific pattern is sometimes tricky because it doesn't always conform to that pattern. So with this, you can actually specify different routes in which you can go. So it gives flexibility on that level. So I think it's better.
Yeah, I agree with that.
Okay, thank you. One more code example, and then we'll be done. Here's number 3. This is again is showing today on the left-hand side and something that you could write. So what do you think the code does in each case? Just think out loud, and what can you tell me? What would your based on what we just talked about, what would your expectation be of the code on the right-hand side?
Well, my expectation on the code on the right-hand side would be that it behaves like the code on the left-hand side does, but it's much clearer to read. Probably don't have to point that out.
The thing is, though, you have to have this defined somewhere, which is probably what the previous slide was about. So if you could actually take this and hide it, so the end users of that interface or object or whatever can actually not care about this and have the luxury of using that, then it's all you need in a language, isn't it? At least in my opinion.
What do you think the accessibility, so public, private, protected, of X and Y and the constructor on the right-hand side are? What would you expect?
Public.
Public?
Yeah.
I think X and...
What?
Why are you hesitating?
So I was going to say that X and Y will be private, but then I don't have a valid explanation why I thought that, so it was just the first thing that came to my mind. And then the constructor for that would be like the point constructor, then that should be public, otherwise why would you have a constructor on that?
So you expected that data members would be private.
Yeah.
And is your experience that's better coding, or is it your normal style?
That's just what I've seen most and what I've had to use most, because you always, like by now, I've always had to keep my private members of the class private, pretty much, so I can have control of them and not let anyone else control them. So makes sense to me in that case.
So what if I told you that the implementation of this particular metaclass, and of course you could write your own that did something different, but this particular one had data members private by default and functions public by default. And you could still override them, but those are the defaults.
Good.
Would that be a good thing, a bad thing?
That would be a good thing, because I would somehow find a way back to the metaclass, and if I needed to know in detail, rather than guessing as I just did, I would actually look it up and see it is that way.
Yeah. So from what you've seen so far, and you've only had a few minutes to see it cold, is this a direction that would interest you in being proposed for standardization, or for it to be developed further?
I mean, the right side, yeah. Yes. Yeah,
Yes,
I think
yes,
I would.
I agree.
Yeah.
Okay. Well, thank you very much for your time. Shall we give them a round of applause? Thank you very much. Thank you. Now let's have a talk. So we appreciate that, but I wanted you, there's a couple of reasons I did that. First is, we're experts. It's hard for us to remember how other people react to new things all the time, especially when we're very familiar with them. I found it very interesting, because I used to resist doing usability studies. I think, why on earth would you do that? Language designers, it's my job to know the right answer and to know the language details. And it's true, you can't just poll users on things about what parts should be where if it affects forward declarations. You have to know some language lawyerly things. But you know, it turns out the car manufacturers have a reason for asking users where the steering wheel should go or what's comfortable for pedals and controls. So I found it very useful, and I've learned something every time I've done this with this particular proposal. And I think this was pretty representative. Let me talk about what metaclasses are. You've seen a snapshot implicitly in what I said. Now let me be a bit more rigorous. The idea is to enable a new kind of efficient user-defined abstraction. Efficient because it's compile time, so by definition efficient. Runtime, of course we want to make sure we don't explode compile times either. The idea is to have a custom transformation from source code to what the compiler sees, to the ordinary class definition. So you can think of it as a way to write give a name to a subset of classes that contain common characteristics that you can code up, and any rules you can write as code is what they are. So this definitely builds on other things in flight. It builds on the richness of C++, the language, classes, concepts soon in the language, if const expr, const expr. But in particular, the reflection proposal that's currently going on, that's championed by Matusz and Axel Naumann and David Sankel, and also the compile time programming proposal that you've heard from Louis Dion. He's writing an update of that. I'm going to assume those exist, even though they're still in flight and they're still prototyping, but we're coordinating with those and other members of the committee and saying, well, what can we build on top of that? So I'm not going to explain the reflection and compile time programming proposals. They deserve talks in themselves, but I'm just going to show one slide, and then I'm going to assume them and build on them. So here's what I'm going to assume. If you see prefix $, that means reflect on a type or an expression. And if you see a const expert block, it can be in a function scope, class scope, namespace scope. It means run this code at compile time. It doesn't have to be inside a function. It's compile time code. And if you want to inject something into the enclosing scope, you can inject tokens into the enclosing scope in that kind of brace. And this currently follows the syntax of Louis Dion's paper from the post-Kona mailing. That's the current mailing. And this is all very mutable. We're, as a committee, figuring this out, and as study group 7. So expect lots of things to change, but just this is a snapshot of syntax in progress. So the way the language works is you have source code that you write. It could be a class, could be a struct, and that gets converted by the compiler, applying rules to generate functions, such as for this first class, you get copying by default, and you get a default constructor by default, and move operations. It also does default accessibility. So for example, int x and y are private by default in the class, but would be public by default in the struct. And then it also changes struct to class. Some compilers disagree that those are supposed to be equivalent, but nevertheless. And if you say struct, then public is implicit for the accessibility of bases and member functions. Oh, and by the way, if the base had a virtual function with the same signature, C++ has forever said it's implicitly virtual. And so the pseudocode you see in the middle is roughly what compiler writers do. They say, for every member, oh, if there's no access specifier, if it's a class, make it private by default, otherwise make it public by default. For every function, if it's virtual in the base class, but it doesn't say virtual, we'll make it virtual. If it's not virtual in the base class, but it's specified override here, emit an error, does not override the base version, and things like that. You know, calculating no accepts and things like that are all language rules today. And I have just one question, and the question is this. What if you could write your own code here? Treat it as ordinary code, share it as a library on GitHub, test it with unit testing, do all the things we do with code. And I want to be very clear, there's nothing too crazy. It is a hook. We're exploring a hook specifically at this point of a compiler, where we translate source code to the AST and basically interpret its meaning in a way that currently is hardwired into the standard for class and struct. We are not doing anything to make this a mutable language. You cannot change the grammar of what's on the left-hand side, nor can you see the slides. There. Nor can you change declarations after the fact. Once a class is a class, reflection is read-only. It is only not read-only here because you're in the process of transcribing it for the first time. But we are creating the ability to on the fly, make data structures, but not to change data structures that already exist. So those are the guardrails here. Just a hook for this. That's all we're talking about. The idea is that $class, or whatever the syntax ends up being, this is just the current straw man. There could be very good reasons not to use $sign because a lot of scripting and other languages use that generate C++ code, so maybe we'll pick something else. Doesn't matter. It's just syntax. $class interface has code in it like that you saw that implements whatever rules we want, and then that you could say it instead of class as a more specific word than class. It still generates a class. There is no bifurcation of the type system. All classes are still classes, but it's just more specific than class. Typical things you do enforce rules like all functions must be public and virtual, provide defaults if the user didn't specify them, and provide implicitly generated functions. But you could do anything, including take what the source code wrote, if you're implementing, say, a compile time variant type, say, oh, let me enumerate its member variables, calculate a buffer big enough and with an alignment sufficient for all of them, remove them and put the buffer in instead as part of transforming what the user wrote as source code. We'll see a small example of that in a moment. So the user code that for something like interface, we've written interfaces for a long time. we call them ABCs. We give them cute names because there's no name in the standard for them. So we say class shape with all public pure virtuals. If we read this and we know, that's an interface, after we've read everything. Now, the reason we have range 4 in the language is because we know how to read for auto I equals begin, I doesn't equal n plus plus I, and we are so good at reading it that we read it without actually reading it, and we assume what's there, and we don't look in the body to see if maybe something changed. There's a lot to be said for declaring your intent up front, and that's what is happening here. On the right-hand side, it means the same as the left, except that on the left-hand side, if you wrote in a private member variable, the code would compile. But it's not what you intended because there was no way to express your intent or the rule. Whereas if you tried to add in maintenance a member variable on the right-hand side, you would get an error with the code that I showed. Now, nobody's taken anything away from C++ programmers. If you really wanted and you really meant to write that member variable, that's fine. You just change interface to something else, but you are just consciously being reminded that you are changing the kind of class you're writing. You have the ability to do it, but it's not going to happen to you silently, that's all. And a convenient way to, with one word, opt into a bunch of defaults and of code. So this is the code that we saw before. The idea is that this code, with the annotations here of what it does, is run against what the user writes in source, so that code runs on this and does whatever the code says in this context per block. One of the nice things, I think, about defining a feature like this is that not all, but many language-like features could be written as libraries. They can be read as source code. If you want to know what it does, instead of cracking a book, you open the source code. You go to definition. And if you want to know if your standardese has a bug today, you call Jens Maurer. And you're in the queue for Jens, or Richard Smith, or someone like him. This you can unit test, just like code. And the hope is it will lead to higher quality specifications as well than we have to do for standardese. If you want to test standardese, you wait several years and then pay Perennial or Plum Hall for their test suites, or write the equivalent test suites yourself. And I'm going to argue that as far as I can tell, there is no loss in usability, expressiveness, diagnostics, performance compared to other languages that hardwire them as built-in features. Now, you might believe me on the performance because, it's all compile time, so of course runtime efficiency. But expressiveness, diagnostics, really? Well, let's prove that out. But first, let me compare it to C#. In C#, if you actually open the current C# spec, you will see this. This is a screenshot of the current C# spec zoomed out in Word. And it's 18.5 pages of English. And I believe that the right-hand side, I could actually make it strictly identical. It actually allows a bit more than the left-hand side does, but I could make it do exactly the same. It is very close to identical, and I could make it identical in about 10 lines of testable code that I could share as a library. I like that. Besides, we're C++. We like our compiler, so being able to talk to our compiler, we probably dreamed about this. And so this is the implementation of interface in the two languages. Here is what the programmer would use. The difference is that, yes, in C++ you write a semicolon. It's the way it is, because you might declare a variable, blah, blah, blah. Oh, by the way, you can still use C++ features like const, which you can't do, which aren't available in C#. But just to compare these, just so you don't believe I'm making this up, I mentioned there was an implementation. It's very alpha right now. It won't compile all the examples that I'm about to show you yet, but it will compile this one. And I have it here, but first let me show you C#. Is that all right? Good, good. No pitchforks. This is a multi-language conference, best kind. So when we look at interface shape, here is pretty much what we saw on the screen. And look, it compiles. OK, that's kind of a boring demo, so let's do something different. Let's say we make this function private, and I'm tempted to write colon here, but you can't do that. So I'll just say it without the colon. And then you get a red squiggle, and the squiggle says, in more or less the words, methods on an interface can't be private. I don't know why well, I do know why they didn't just say that. When you're a compiler writer, you're talking at the grammar level, language rules level, so generally there's a temptation to have general diagnostic messages of the type of like, grammar thing this can't appear in grammar position y, and so you get this kind of diagnostic. I mentioned, here we have in Compiler Explorer, thank you Mad Godbolt for making this available. So it's up there in Compiler Explorer in an area. But here is the same source code I just showed you. Now, Andrew's implementation still uses the pre-Kona version of ... He's in the process of removing that because 6 weeks ago at our standards meeting, the group decided they didn't want the ... So we'll remove it. But for now, that's what it takes to compile. Otherwise, I believe this is identical to what I just showed you. And so here are the, oh, but I don't have an interface. Well, why don't I just copy the code from C#? Oh, but we can't just copy and paste code from C# to C++, can we? Well, I'm an optimist. And I've tried it already. And now, if we show the diagnostic, oh no, there's red stuff on the right-hand side. Whatever could it be? Ah, well, first of all, we don't like the private, so let's take away the private, because we would have to have a colon there anyway. And now, as it waits to expect a qualified ID, oh yeah, in C++, I have to write a semicolon. If I add the semicolon, it compiles. Now, what does it do? It turns out that Andrew's implemented a nice handy little thing that says compile, not just .require and .error, but compile .debug. Like show me, just reflect and pretty print what shape is. So let's take a look, and there it is. Let me just scroll a little bit so you can see. And just pretty prints it. So it's taken the functions that we've taken, it's made them pure virtual, it's applied the rules we said, it added a pure virtual no except destructor, and then if you scroll down, you'll see the constexpr program because the whole thing was injected into shape, including the constexpr code that runs there, and that's how it validates shape. But we got an error message when we tried to make this private with the C# compiler. Let's just take a look at that. So going back here, to interface shape. Let's make this private. And we wait for a small compile. Error interface function supposed to be public. Let's compare the error messages. I'd say we're at least equal. Now, what else could we do? Oh, what else could we do is we're not allowed to have data members, and C# doesn't like that either. So now if you have to look at the squiggle really close because it's a short variable name. I wouldn't normally make that, but interfaces cannot contain fields. Ah, wonderful. That's what member variables are called in C#. Nice error message. Can we do that here? So I'm claiming that we can do this, we believe, with no loss in usability, expressiveness, diagnostic quality, or performance compared to other languages that have this built in. And this is not just because it's a bright idea now. It's built on a strong foundation. It's because Bjarne Stroustrup made sure he did not bifurcate the type system. It would have been an easy mistake to make, designing C++ in the early 1980s, to say a class is something different from a struct, and he wisely did not. And he had people coming to his door regularly for years saying, just make them separate. And he refused. A struct is just a class. Every kind of class is just a class. That's one of the underpinnings that lets us say an interface is just a class, because class is already general enough to express all of these things. It's just that struct was sort of the first example of how you might have a different set of defaults, class and struct, where you might say the first two metaclasses that led the way. One for backward compatibility, and one for what we would prefer going forward from what we knew as of 35 years ago. So that was important, and it shows a difference in our philosophies in the languages. C# and Java like having special purpose language features, and usually you can do very high diagnostic quality that way, and you can give users a simpler language. We prefer to do, instead of a lock block built into the language, have a lock guard and have a general feature, RAII, stack-based destructors and stack scopes. And the nice thing about this is, yeah, you put the brace first. Get over it. By the way, notice as of C++17, I don't have to say arrow, angle, mutex, angle here again. So this is C++17. And it fits on the slide better for that. I can use a bigger font. But I can put anything. If I want a time block, I can just make my own time block that has a destructor. And the constructor waits for the lock, and the destructor does whatever. And I can do that here, and it's the same. In C# and Java, you have to abandon the synchronized block, or the lock block, and write your own type that has a destructor. You have to basically cobble it together the way that Java and C# half support RAII. You have a dispose method, and then you write in C# the using statement, or Java now has inhaled the same feature as a try with resources statement, and you can get the same effect, but you have to opt into it, and it's basically still not the lock block. You have to abandon the narrow feature because it was a narrow built-in feature. The other thing is, I can make a time block and give it to you as code and put it on GitHub, whereas if I had an extended lock feature, I'd have to wait for Java 13 and wait for my compiler to update it. So the idea of value is similar. This time it's a metaclass that will enforce. It has copy and move, comparisons, default construction. And this is optional, but I happen to prefer, so I wrote it this way as a straw man, private data, public functions by default. It's what we teach people nearly all the time anyway, unless it's an aggregate, in which case I can write an aggregate metaclass in a few lines if we want that. And that also enforces no behavior, no destructor. And enforce no virtual functions for this. So here's the code for that. Because in the Great Standard East tradition, we want basic something. If we're going to reuse it, I'll make it a basic value. It has those 5 special member functions by default. Oh, by the way, I should add, if you're applying a metaclass, like you say, instead of class IFU, you say interface IFU, the idea is you replace the compiler's defaults. So it means that the standard is implementation of class, which gives you special member functions that are generated for you, implicit virtual, all those rules do not apply by default. We use the metaclass's rules instead. So here, that's why I opt back in to explicitly say, no, yes, I do want these 5 special member functions. It's always going to get a destructor. That's the only special member function you always must have. And I'm going to make variables private by default, functions public by default, an error if you have a protected or virtual function, which doesn't make sense for a value type, and say that the value destructor must be public. It's what we teach people today, so I'd like to say it in code. And then a value is a basic value that is also ordered. I just wanted to factor ordered into a different metaclass that generates the comparison functions. And if you've been following, I'm also doing a proposal for generalizing comparison functions and simplifying those. If that is accepted, so far it's looking good, but you don't know until you're done. If it's accepted, that would just be a detail inside the implementation of ordered in one place. It would simply work better with that new comparison operator that's being proposed as well. And you use it just by saying value point int x equals 0, y equals 0, point int int. And yes, it's default constructible. Yes, it's copyable. Yes, I can equal. Yes, I can put it in a set which requires less than. So that's the idea. But I opted into that by simply saying value. I mean, the most important book I've ever read in my life in the software world was Design Patterns. Sorry, it was not a C++ book. And I know it's been much maligned, but it shouldn't be. Because when that book came out, it was the first time in my life I had ever gone to a bookstore, just randomly on coffee break, seen a new book I did not know anything about at the time, opened it, and within 2 minutes knew I was holding a classic in my hands. Because it gave you names for things. Instead of talking for 3 minutes to describe a class that does X, Y, Z, and so forth, singleton, visitor, message, all these things, and factory. And even if you don't like the pattern, having the name is powerful because you can say, don't do singleton. So let's see the value of the name regardless of the connotation. I won't ask you to read this from your seats, but this is class pair. Just the interface, not the implementation. Quiz, what kind of class is it? What can I can't do with it? You read the code or you attend library working group. And what I would like to do is you still have to write much of that, but I would like to do it in one place forever. Write it just once in let's call it literal value, that is a value, but it also gives you explicit constructors, const expr functions, a make function if you still want that with C++17. You don't need it, but maybe for backward compat. Piecewise construct usings, I can put all that in. This one is important to me because as I've seen pair go through the sausage grinder for the last 15 years, I can't tell you how many times I and many others have asked, why can't I just write something like class pair T1 val1, T2 val2, end brace? And I've asked committee members, I've asked experts outside the committee, library, core, what would it take in C++ so that we could write that? I've never got usually an answer, and the 2 times I got a partial answer, it was mostly, we can't do it for this reason, but maybe someday. This is the first proposal I know where you could do that. Now, it's still, all the glorious things you might want to do are still there. Maybe we can make those simpler with other proposals, but at least I can say it in one place. That's my goal. Here's another example of simplifying language evolution. So somebody might come and say, well, what if we would like a flag enum type in the standard? Well, let's first make a basic enum. By the way, a basic enum is a value. And I'll require that it must have at least one member variable, which I'm going to use as my const expr enumerators. And if the first member's variable type is auto, I'll inject an underlying type using to be int. Otherwise, I'll inject the underlying type using to be the type of the first variable mentioned. Then I'll enforce that all of the member variables are public const expr and of type u by default and cannot be said to be otherwise. And then I'll inject a value. So that's a basic enum. That's very similar to the built-in enum we have today. But I want to do more. I now want a flag enum. So to have a flag enum, I want to do these same things, compose metaclasses, apply defaults, and enforce the diagnostics by saying a flag enum is a basic enum. It has these bitwise functions, and, or, XOR. It has a default constructor, but unlike the other in value, it just said there must be a default constructor. This is more specific. It says, no, the flag enum default constructor sets the value by default to the none value, which I create down here. I don't need the injection syntax because it's not in the const expr block here, so I can just write the declaration. And then in my const expr block, I just compute the powers of 2 values. I start with value 1, and then for each value, I make sure you didn't write a default value because the grammar lets you, so I'm going to force you not to. No, don't do that. Put the gun down. And then I'll give next value times equals 2. In a draft paper some of you have seen, there's also an error check, which I removed just so to fit on a slide, that you don't exceed the number of bits in the underlying type. I'm sure that you can see readily how you would compute that. Size of, and compare it to next value. So we have here a hierarchy that we're very familiar with from classes for metaclasses, and is a hierarchy. And this way I can say with syntax that is very close to actually the C enumeration syntax, but it's a class, it's a regular class. I'll just say flag enum open mode, so that's like class open mode, but with all these rules. Auto, in, comma, out, comma, binary, comma, add n, comma, app, trunk, semicolon. So I think the main difference from C is I put auto and I put semicolon. And I could put a type instead of auto. If I wanted to specify the underlying type, I would just put it here. And then I can say open mode, and I can OR them, and I can assert they're not equal, and I can AND them, and that all works. Now, one of the nice things about this is even as I was writing this up, I made a boo-boo. This I can, again, test like code, and it's just as clean as what I have today in other languages. And by the way, Anthony Williams, is Anthony here? I saw him earlier. Anthony, thank you. Great article a year ago. I am not dissing it, but as soon as I saw it, I compared it to this, which I already had then a year ago in draft form, and created this slide. So you're seeing a slide created a year ago. Sorry. I wanted to demo it too. And the idea is you can get very close in regular C++, but there's stuff you just can't do, and it's a bit more Baroque. You can't generate the powers of 2 values. The programmer still has to do that. And it's not not quite as clean, and it's just more brittle because of the way we approximate it today. So it's actually quite clean for today's C++. It's a very good implementation. I would like to be able to do even these other things too. But I made a bug, I said. I forgot the XOR, as I found in unit testing. It took me 15 seconds to add them. I'm sure that doesn't surprise you. You could probably do it in 7, maybe 6.5, because you just cut and paste and you change the OR to the hat, right? And then your unit test runs. Adding it as standards wording would have taken an hour in EWG and core, and the first time I showed this to a standards committee member in a draft slide privately, he said, you'd never get it through core in an hour, evolution in core in an hour. It'd be at least an hour and a half or 2. Because why? Because if I was doing this as a language feature, as a flag enum built into the language, I'd have to specify it as standardese, and that's hard, and you need real expertise to do that. And Jens Maurer and Richard Smith and others will show you the parts that you omitted and how it interacts with the rest of the standard, and it's not consistent with the way we specify things over here. This is code. I can reason about it, I can edit it, and I can test it. Every single time that I talk about enums, somebody asks, can I print the label? So I made a slide that, of course, yes, you can. Most of this doesn't use metaclasses, by the way. This would just use compile time programming and reflection, but it leverages those very nicely. And we're just leveraging what templates already do. So imagine a 2-string template that is constrained to basic enums. So now I'm using a metaclass, so metaclasses do work here. I would like to use them to constrain templates just like we use concepts. They are very complementary with concepts. Let me just talk about that for a second. We had better get concepts in the language. They are wonderful, and they make metaclasses better. You might think of metaclasses as constructive concepts, because concepts let you query a type, and these let you define types that match a certain pattern. So the key thing, there are the 3 things you want to distinguish between metaclasses, concepts, and just reflection type loop queries. So first you divide the world into read versus write. So if I'm defining a type, that's what metaclasses do. That's the only thing they do, although they have .is and .as to query if something matches. But they're mainly for defining types. For querying types, you can either use a reflection-like loop here, like we're talking about in the future, to just reflect over things and just iterate over the member functions, like does it have copy, does it have equality? Or you can use concepts which powerfully allow basically use pattern matching. And we need that too, because even if I can write a loop, so in the ordered metaclass I did not show you the details of, I use concepts in there because I could write it like the ones you've seen and iterate through a loop and visit each member function and compute things, and you can do that. Because I want to say, well, does the class already have equality? If not, I'll generate it. It's much easier to write a concept that says, can I do with T, A, comma, B, A equal B? Because that'll catch if it's a member or a non-member. Like it already does all that. I don't have to then compute it myself and account for members and non-members. So we absolutely want concepts and reflection-based iteration. Both of them are great for type query, and they both work great along with metaclasses and in their implementations as I query the source code coming to then generate something and make decisions. But what this is doing, back to toString, it takes, for any basic enum E, so I'm applying a constraint, it takes a value of that type, creates a switch statement, and here comes constexpr. And I believe this is very similar to something that Louis has in his paper. You have a constexpr block, which in a loop, compile time loop now, says for every object in reflect on that enum type and its objects, if it makes sure it has a default value just to sanity check, then inject a case statement. Case, if it's that default value, which I then unreflect the value back into source code. Return, I unreflect the name back into source code. And so basically all the constexpr and its loop does is it injects the sequence of case statements, 1 per enumerator. And then I can write this kind of code, and I get toString. Every time in the past that somebody has asked C++ to be able to print string enumerators, we have said no, and we were right. The reason is because that is the camel's nose of always on or default on metadata. And we don't do that because we are a zero overhead language. It's not wrong for the languages where that's their design point. They should do it and can do it and do. but we are zero overhead. Don't pay for something if you don't use it. And default on metadata that includes all the enumerator names and strings in your XE image, whether you ever look at them or not, that's not who we are. That's not what we do in C++. Now, having said that, we want the enumerator names, so we're kind of envious. It's just, we want to go to that part of town, we just don't go there. What we can do is templates, which already have a very nice feature of when they're instantiated. Remember when templates are instantiated? Only if they're used, which means this is a template. And so toString of x for any given type x is instantiated on demand at compile time, no runtime here, only in calling programs that actually use it, not in the library you're shipping, but in that particular end user's program, and only for those enum types that he ever asks about in his executable, which means you can ship a library that allows people to fully reflect over their enumerators and the enumerators in your library without having their names in your library at all. But they're available, except in the source code, but not in any object or anything, and your users still have access to it. Of course, if you use it, then it's in your object, but it's only when you use it. Now, here's another example. Let me just give you a couple of Segway examples and then close with what they lead up to. We have had properties proposed for the standard. And again, like interface, properties might stand a better chance, but I don't think we would ever standardize interface. If we would have done it by now in the last 25 years. But it's too narrow a language feature to spend another 20 pages of core text on, right? Is it worth it to add that much again to the language? But I could see adding it as a library. Similarly, properties have been proposed before, but they've never really got much traction, even though clearly there's a use case for them because people keep reinventing them. So instead of on the left-hand side today, we have a coding pattern. We have a member variable with a value. We have a public setter and getter. And then on the right-hand side, now, if you look very carefully, this is subtle, there are two metaclasses. There are two classes being defined. I'll talk about class X in a minute. That's the enclosing one. Value is a nested class. That's like class value. So a metaclass can be templated. So in this case, I'm saying, oh, property is a metaclass which takes a parameter, the type, which is t. So property int value, and that's why you have brace, brace, semicolon at the end, is because you're defining a type. Well, that's not what you want. You want a value in there, right? So that gets you most of the way because property, I will just summarize briefly, lets you write an underlying type and a getter and setter if you want. You'll see it on the next slide. But by default, if you just say property event, just like in C# and other languages, we'll say, OK, if you didn't ask for anything else, by default, I'll give you a member variable of that type and a getter that takes it and sets that, and a setter that reads it and returns that type. I can do that by default. But that's now a nested type. It's not instantiated yet. So that's why I have the outer one. So if I have, say, class X, so not class, but a metaclass that knows about property, all it does is iterates over the data members. And one of the things it does is, or member types, it says, oh, if I happen to see a nested type of type property, I take its member variable and functions and inhale them and move them into the enclosing class and get rid of the nested type since I don't really need it. It was just a helper. So that metaclass pulls it up one level, and now you have the left-hand side, exactly the left-hand side, but you wrote it like this. Now, if you wanted to write your own property, you could, for example, have a property of int, so it advertises to the world it's an int. You can get an int and set an int, but we really store a string. That's fine. So now I have to do it myself, though that's not the default. So I have a property of type int that contains a string value, and it has a set function that takes int, and I can enforce that at compile time, and a get function that returns int. I enforce that at compile time. And I may or may not bother looking at the internals of the functions, because either they compile or they don't. As long as you return the int that you said you would, I'm cool with that. And again, I can enforce things about this, that there's only get and set functions, not something else, that the types match, or that are convertible, things like that. So now this is what it's leading up to. there are frameworks out there, and I built some of them, that I never want to build again. So let me start with Qt, and then I'll talk about C++ CLI and C++ CX, which I led the design of. And part of my motivation for this is I had to do those as non-standard extensions because the language was not flexible enough to say what needed to be said. But I never want to invent those again. Life's too short. I have other things I want to do. So let's start with Qt. QProperty is a macro. I've tried to build the macros because they're so important. The QProperty is a macro that basically cobbles together. It assembles the information about that's missing. There's no abstraction below, so sort of gives you the abstraction that's intended. And it assembles those things, where on this side I can just say a property. I can talk about it as a first-class thing that is a metaclass. It is something that is enforced in code. It's a new user-defined abstraction I can talk about, instead of a non-abstraction that I annotate what parts are supposed to go together, which isn't enforced by the compiler. And if I want to have a property of a different type, I can do that. I believe this example is taken on the left side from the Qt documentation. And yes, you can have your own overridden getter and setter, same as before, that have a different type or do a computation. So Qt, how many of you have used the Qt and the Qt mock compiler? It's a great tool. People regularly complain about it, but the reason the Qt company, Trolltech, and everybody have built it is because it's necessary. Because you can't express what you need in just C++. So the idea in Qt mock, their model is you have a .h that is a superset of C++ with macros. You compile that not just through your regular CPP, because the macros make the bad stuff go away, and then it looks enough like regular C++ you can get it through a C++ compiler. But you also put it through the mock compiler, which generates more CPPs that you feed through here, that go through the C++ compiler. And they also generate metadata and for objects, enumerator names, anyone? And things like that. And you need the separate compiler because the basic problem is you need to put the extra information somewhere. You either put it into the C++ source, which is the option they've chosen here, which means you need a separate side, and then you can have to put a compiler that understands it somewhere, in their case, a separate side compiler that parses out those parts and does something with them that are not in the standard language. I would like to be able to write this. I think everybody, including the users and suppliers of this, would like to write this and would have if they could have. So here's a sample of Qt mock and how I'd like to write it in the future C++. Instead of having to derive from a public Q object, Q class knows to do that. That's a metaclass that can just say, oh yeah, and if I'm a Q class, of course, I implicitly inherit from Q object publicly. I do whatever the Q object macro does. Read your header for details. I give it a constructor that has a parent pointer. If I have a property, we already saw property, so same thing, just reusing it here. And Q class would know about property, so it inhales it and makes it be the same as the left-hand side. And signals and slots, these are interesting because it shows the power here. They're tag types. So signal is just a type. It's not a metaclass. It's just a type in like the Qt namespace or something is the idea. And when the Q class parses it, it says, oh, look, the return type's a signal. How handy. I know what this is. But I haven't changed the grammar. I'm just using the return type position and a well-known to me type to signal a special value. So without a grammar extension, I can implement a kind of language extension in C++ without a separate compiler. Because signals can be invoked, signals usually have void return types in Qt, but you can have a non-void return type for signals and slots. So for instance, you can invoke it directly instead of through a slot, and therefore the return type can matter. So the way I've written it up in the draft paper is the signal is a ordinary type, but it's templated on the return type, which defaults to void. And thanks to C++ 17, I don't even have to say signal angle angle to get the implicit void, because with a deduction guide, I can get the implicit void. And I get some really clean syntax out of this. And similarly for slot. Now here's what I bear some responsibility for. So same idea again. We needed more information for C++ CX for WinRT. Same thing applies to C++ CLI. So you have a header file with extensions that nobody else knows what they mean if you're not on a Microsoft platform, and most of those are still, don't like it either. And then you have a CPP file with those extensions and a C++ compiler with extensions. This won't work on Clang, or GCC, or whoever, the ZapCC, whatever the latest is. But then we can generate the WinMD stuff in the object. The reason we did this is, and by the way, of course, I'd rather do it all with one tool chain that can emit the same end result. The reason we did this is because the other option is what COM did, and what Windows is currently replacing C++ CX with, is going back to the COM style. So to make it a bit more C++y, it turns out you can do that for consumption, but not for authoring types. You can put the extra information away from the C++ source, but then it's in like an IDL-like file that requires an IDLE-like compiler. And again, you're in a Qt mock-like tool chain here. And again, I would like just this same picture. We just run the source through and write it as C++ using compile time programming and metaclasses and generate what we need. So here's a draft. This syntax may change, and we're still figuring out if this works. So I mean, everything I'm showing you looks hopeful. I can't 100% tell you that it actually works yet, but it looks promising. The current plan is to be able to write something like the right-hand side instead of the left, and not in a separate IDL file, and not with a separate compiler, but just through the regular C++ compiler. And if metaclasses or something like it, some evolution of this, were standardized so you could write the right-hand side, it would just work in GCC and Clang and everything, without something vendor-specific and non-portable IC and GUI code. The only thing I forgot here, you might notice again, is the semicolon. It's OK, my compiler will tell me, and then I'll hit the button, and then it'll go. Notice some of the stuff that we're doing here. You saw property, so right now, the way you do that in IDL is you annotate property, get and set. Notice that because every COM method must return an H result, you don't have a place for the return value. So the way you do that is you have a star out parameter, or an extra star out parameter that you mark as out ret val. Metaclass code, compile time code can easily look at this and say, oh, look, I'm in an RT interface. That means it's going to be COM-like. Any function I see, such as the property getter, if I see the return type, I'll just take it, move it to a parameter, add an extra star, and replace the return type with H result, because that's what COM does. And I can just automate that. So I can read this the normal C++ way. It means the same thing, and this generates that. And then the same for, and also for generating this ret val attribute. So I can do all this as just compile time transformations. And yes, this means I have to be able to also, in general, in other cases, reflect attributes. So anything in the source code we should be able to reflect. So my goal with this is to try to do two things: to make C++ more powerful and to make it simpler. That sounds like an oxymoron. There is only one way to make something more powerful, language or any product or any tool, and simpler. And especially in the context of a programming language, the only way you do that is by adding abstractions. And there's two kinds of abstractions that you might add. One way, which is good, is to build the language abstraction into the compiler, so like range 4. So it takes a coding pattern that's done by hand today, and you can actually declare your intent in the language. But it's a special purpose feature like range 4. It only works for that one thing, but it automates that one thing really great. And some of these are very general, like templates fall in this category, because they're parameterizations of things. They don't really hide stuff. They're parameterizations of existing extensions, existing abstraction mechanisms. But the great way to do it, and the thing that has made C++ and other languages successful for decades, is by adding a new way for programmers to author their own abstractions. And by abstraction, I'm going to be very specific. I mean something where there is a separate implementation and interface, where you can hide implementation behind an interface. So templates aren't that. They're a parameterization of the two that we have. Today in C++, we have exactly two of these. We have functions and we have classes. Those are the only things in C++ where I can author an interface and hide an implementation. With a concept, I can write the concept and say what it matches, but I'm matching things. It's very powerful. We have to have it. but it falls in the same category as templates. It's parameterizing how we use abstractions and deal with interfaces. It doesn't define a new interface and hide new implementation itself. In fact, the only thing currently underway for standardization that would be such a new boundary is modules that I can think of. Correct me if you can think of one that I can't, but modules let you say a new interface and hidden implementation, and that's one reason why they're so game-changing and enable things like package management and other things. They're a necessary tool to do other things, because as soon as you give somebody a new way to write their own abstraction that is an interface that hides an implementation, wow, with just classes, how many languages and tools have we shipped for 30 years in the mainstream, and how much better our code is? Those are powerful. You don't need many of them. You need good ones. We've been missing modules other languages have had, so we were adding that one. This would be another one in that category where I can write an interface, hide implementation, make it reusable, and share. So my hope is, again, we look at encapsulation. That's what these do, interface and hide the implementation. And my hope is that we can expand C++ abstraction vocabulary beyond class, struct, union, enum, which are the 4 we have today, to enable, one of the things I've learned doing these usability studies, only with a few dozen people so far, is that every single person I interview, nearly everyone says, here's how I would use it on my current project, and the answers are nearly all different. Some would use it to enforce coding standards that they require in their shop for some reason, compliance reasons, regulatory or whatever, or just because somebody doesn't like certain styles, whatever. And others, one other example was they were using a hardware machine interface library that required classes to follow a certain structure, and they had to write it by hand today, and if they got it wrong, they didn't get errors, and sometimes programmers didn't want to follow it, and here they could just write that boilerplate as a metaclass and enforce when they get it wrong. So it's a powerful abstraction mechanism, and it's actually a good sign, I think. Bjarne Sturstrup is very wise when he says he does not want to build a language feature that he can only think of the uses for. He wants to build one where he can't think of, people can think of uses he never thought of that it solves. Classes fall in that category with all of their accoutrements, virtual functions and templates and everything that parameterize them because they're so general and solid. If we can do the same thing for compile-type programming, that would be awesome. I would love to relieve evolution working groups' workload. If we could ship more standards proposals, not all, but more what are now language proposals that are very hard to understand, to write correctly, and increase the breadth of the language, and make them libraries. They're cheaper to standardize, you can test them, they're higher quality, and you can share them and try them yourself without waiting for your compiler vendor to do something and ship it for you. And I'd like to never write C++ CX and C++ CLI again. So I hope that users will be able to, I hope that someday we'll be able to be in a world in C++ where users don't have to wait for a compiler. They can use new language features, share them as libraries. You know, what would have otherwise been new language features, some of them, can add productivity features themselves. I hope we can treat more features as libraries and standardization. That would make evolution easier, and higher quality proposals if we can unit test them. And if you're a C++ implementer, I know you'd love less work to do, and you can catch up on some of the bugs, right? So fewer new language features, less compiler work, and we can also, did I mention COM and C++ CX? It would be nice if we could deprecate and then over time remove support for large classes of extensions today. That would save us money, because all the extensions are necessary, not always loved, and they need to be supported. So the more we can do in the standard, the more we can do for portable code, that would be nice. I'm hopeful about this. I will try to give updates. This is a beta talk. You are the first public audience I've spoken to about this. I have asked the organizers to please just not distribute the video until after we've had a chance to talk about it at the standards meeting, for politeness, not to get ahead of ourselves. But since I had the opportunity to talk to you here at ACCU, I thought, you know what? The reaction so far to some of the parts of this that have been in the standards committee so far with the compile time programming and reflection parts has been positive enough. I'll go out on a limb and share this with you. But let's see over the course of the summer or the next year, how that goes. I will in time announce where you can publicly try the implementation on godbolt.org, and it will be an open source implementation. It's a Clang fork right now that's being written. And so I hope that we will get to a world where this is one way that we can continue making C++ more powerful, because we don't want to dumb it down. But we also want to make it simpler to use and more robust and correct and less tedious. And those two things I don't think need to be in conflict. I would like to get both, and I hope that you'll be excited about the future of C++ with this and many other proposals happening. And thank you very much for inviting me. Thank you for coming to the conference, and thank you for your time today.